Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 19th lecture of the course Marine Renewable Energy Systems. Myself and Dr. Patil are handling this course. This is a SwayamPrabha course offered by Department of Maritime Engineering at IIT Gandhinagar. In lecture number 19, we will continue with the numeric model in time domain using WEC-SIM-II. So let us say, what is a weakly nonlinear time domain model? We already saw in the last lecture the details about time domain model. Let us say where is the weakly nonlinearity comes into play. Now first let us understand where the nonlinearities come from. What are the sources? They can come from wave device interaction, which includes the geometry of the system, the order of the wave theory you are using, can also come from the mooring stiffness, it can come from PTO damping, can come from second order terms of diffraction and radiation potentials, can also come from nonlinear Freud-Kraloff force. So these are the various sources of nonlinearities which generally come into play when we do analysis. Suppose if the nonlinearity associated with the Freud-Kraloff force is considered in the formulation, then we call this, then it is referred as, let's say, only if only the nonlinearity from Freud-Kraloff force associated is considered in the analysis, then it is called as weakly nonlinear time domain model. Therefore, the order and complexity of nonlinearity, of course, is a trade-off between the cost of time and computational effort. It is observed that the nonlinear terms coming, the nonlinearity coming from Freud-Kraloff force are predominant. It is observed in the literature that the nonlinear Freud-Kraloff forces are predominant in wave energy converter designs with non-uniform cross sections. For example, the bean shaped cross section is a non-uniform cross section. So, Foley in 2016 observed this and stated that. Therefore, friends, in linear wave theory, the wave potential is not defined above the still water level. Okay, if you say this is my water depth, this is a seabed, and this may be wave profile. Wave profile is defined only still the mean sea level. Above that, it is not defined in the linear wave theory. Therefore, friends, the linear model represents frequency domain and time domain methods based on boundary element method or panel method with lower computational efficiency. Okay. So, in the weakly nonlinear time domain model, Wheeler stretching is adopted. So, the surface profile is extended as per the actual submergence levels, and we call that as Wheeler stretching, which is expressed and observed by Wang et al. In 2020. So, therefore, friends, the Freud-Kraloff force in time domain can be expressed as Freud-Kraloff force St, which is a variation of time, plus Freud-Kraloff force dynamic is variation of time, which can be said as Fg minus surface integral of P static n ds minus surface integral of P dynamic n ds. Equation number 1. Therefore, for considering only one active degree of freedom, I can always write the effective equation of motion for the model as m minus a infinity x double dot t plus minus infinity to time k r t minus tau x dot tau d tau plus c p t o x dot t plus k m x of t, which can be equal to now f g minus surface integral p s n ds minus surface integral p dynamic n ds and so on. We call equation number 2. Now let us talk about pure nonlinear time domain model. The above equation that we discussed will be modified. So, the equation 2 will be modified to accommodate the higher order wave potentials. So, that makes the model fully nonlinear. So, this is useful to estimate the excitation forces coming on the system, but the accuracy will increase, no doubt, but the computational cost will also be parallelly more. So, in that situation, the instanted wave Pi, which is said as minus rho dou phi dou t minus rho del Pi square by 2. The diffraction wave Pd is minus rho dou phi d, let us say this phi I, okay, phi d by dou t minus rho del phi d square by 2. We call equation number 3. The radiated wave Pr is minus rho dou phi r by dou t minus rho del phi r square by 2. Okay. Generally, in wave energy devices, people go up to weakly nonlinear time domain models. Let us comment this, saying that in WEC designs in time domain, researchers prefer to stay with weakly nonlinear time domain models. Okay, that is what general observation, what people have seen in this. Let us see what are the computational tools we have to do this. Now we have different tools developed by Sandia National Laboratories. Which is SNL, and we also have, of course, NREL, that is National Renewable Energy Laboratory. So both of them together developed a tool called WEC-SIM. It's called Wave Energy Converter Simulator. Okay, this is a very useful tool which generally used in the modern era to assess WC. This is used to assess wave energy converter in time domain. Okay, both linear and weakly nonlinear. Now, what are the advantages of this? This WEC tool or this WEC-SIM is an open source code. It has got reduced simulation time, and of course, the simulation cost and effort is also reduced, and accuracy is acceptable. So, let us see how this work tool looks like. So, this is how the work tool looks like. All components are logically interconnected. Let us say the work tool is what you see in the screen here. The floating wave energy converter geometry is defined. It is taken to the WEC-SIM input file, and it is now done into a time domain Simulink model to analyze the system, which we discussed this earlier in our previous lecture as well. Friends, let us see how the WEC-SIM flow diagram looks like. The wave energy converter exciting force gives an input to the wave force coming onto the system. The system also receives the input from the mooring stiffness. The system also receives input from the PTO damping, which comes from here. The system also receives input from the radiation damping coming from the system. So now this becomes the total force coming on the system, and the system will now undergo oscillation and excitation. We work out the excitation coefficient from here, and the acceleration velocity is used and displacement is computed, and from this the energy is computed. So friend, this is a simple dynamic model of WEC in a Simulink platform. Okay. Having said this, every level of analysis requires iteration to maximize the absorbed wave power. So our job was to maximize the absorbed wave power and the overall efficiency of the device. Okay. Now we understand that the overall efficiency also depends on the performance of the virtual PTO, because the overall efficiency in real PTO is going to actually control the device performance, but we induce that in the overall design by including the damping coefficients with associated parameters in the design. Therefore, friends, to compute the effect of the virtual PTO with that of a real PTO, we need to conduct experiments. Of course, on the scaled models. Okay, so this effect then can only be transferred to this. Now let us see what are the variations which we can include in the virtual PTO coming from the real PTO in terms of multi-body dynamics. Variations in design in multi-body dynamics. Now instead of having 4 floats, one can go for 6, 8 and 10 floats. Now when you increase the number of floats, the damping factor on the virtual PTO should also need to be estimated. You cannot have the same damping factor which we use for the 4 float analysis for successive 6, 8 and 10 floats, etc. Let us see how this arrangement looks like. So now the arrangement of the floats vary as you see in the figure here. Initially we had only 4, now we have one arrangement, let us say, which is 1, 2, 3, 4, 5, 6 floats. Another arrangement has 1, 2, 3, 4, 5, 6, 7, 8 floats. Of course, we do not have figures for 10 and 12 as shown on the screen here, but in all these cases please understand the wave direction is chosen in such a manner that the capture width ratio remains maximum for the chosen direction. Wave is not hitting here, okay, in all the cases. See, this becomes the wave direction. So, the capture width ratio remains maximum for this. So, one has got to be very careful in choosing the layout geometry with respect to the wave approach angle to get the maximum power. That is another important point what we must remember when we talk about the working principle to harness the energy in multi-body dynamics. So, therefore, when multiple bodies are connected to this, even the draft of the central buoy need to be also altered. So, we have to have an arrangement of ballasting, deballasting the central buoy in such a manner that the central buoy possesses the desired aerodynamic characteristics as a free float which can handle many number of buoys, not only 4, 6, 8, 10 accordingly. Therefore, friends, the float design which fixes the number of floats, the float design which fixes the number of floats can alter the natural frequency of the device. Therefore, the operational range of frequency of the device is also now changed. Okay? The capture width ratio will also now change. Therefore, the virtual PTO damping need to be worked out accordingly. However, one advantage what we have here is The floating devices will not be and need not be designed for its strength base. Instead, they should be designed on displacement basis. Now, this is where the design concept varies for multi-body dynamics. This is generally known as form dominant design. Okay. Now, we have to also check the recentering ability of the platform or of the device with multiple floats. The mooring stiffness of the central buoy need to be altered so that the buoy floats positive and the buoy remains positive buoyant for the entire design. Okay. So, more details can be seen from the research papers what we published and the patent document what we have. Now, interestingly friends, multi-body dynamics of different floats also has references in design from wave bob, from wave star, which are all floating energy devices which include multi-body oscillation, and they harvest on the relative motion between the multiple body and the central. Okay. For example, wave bob is a two-body wave energy converter. Wave energy converter which has got your torus member and the buoy moving in the vertical direction. So, you can see more details from Tarant and Mescal. Paper published in 2016 about wave bob. Wave star is a near shore device which has got an hemispherical buoy and heaving around a fixed base structure. You can see more details of this in Hansen and Kramer, published in 2011. Now, let us move on to the detailed numerical model in WEC-SIM as we see here. So, the WEC-SIM model can solve multi-body dynamics. With WEC systems and PTOs, and of course attached with the mooring because the central buoy is actually moved. So, there are various inbuilt tools available in WEC-SIM in the simulator which can help you to develop this. The geometric data and frequency dependent parameters such as hydrodynamic coefficients should be obtained from the boundary element formulation in aqua, and that should be input to this. That is very important. So, the hydrodynamic coefficients and the geometric parameters should be obtained using boundary element method in aqua, and that should become an input for analysis in WEC-SIM. Okay. In addition to that, one should also have the mooring and the PTO mechanism parameters as an input for the WEC-SIM model. So, PTO mechanism properties and the mooring stiffness characteristics should also become an input to WEC-SIM model. Now, the equation of motion expressed in time domain for the whole device, for the complete device, with 6 degrees of freedom. Ideally, you see, we used 3 degrees, that is surge, heave and pitch. Then we move on to heave and pitch, assuming that surge cannot be damped, need not be damped because it is recentering problem. Then we said pitch and heave are coupled and dependent each other. We need to apply radiation damping and the external damping, we said heave. So, we modified the equation of motion to single degree ideally to solve the problem frequency domain. But this issue is not that simple and it can be taken to a higher complexity in WEC-SIM model. So, you can handle full 6 degrees of freedom problem and then it is solved using 4th order time step Rungo-Kutta method. That is the solution procedure adopted in WEC-SIM. So, therefore, friends, the body coordinates need to be discussed and fixed in the problem formulation. The rigid body motion of the device is expressed in standard coordinate system which is XYZ and is defined at mean sea level. Okay. The local body coordinate system which is used for the floats can be expressed as XYZ, which is defined for each body present in the system. Okay. So, there are 2 sets of coordinates we are handling here. For example, if each float is positioned to oscillate about YV axis, then the orientation and position of that can be transformed to rigid body using transformation matrix. Okay. Therefore, a typical equation of motion based on Cummins equation for heave degree, which we already wrote, I am rewriting it with a replacement. So, initially we said Z of t is now replacing x of t because I am using only heave motion. So, I am now writing m plus added mass Z double dot T plus KH ZT plus integral minus infinity to T, the memory value, the memory aspect, T minus tau Z dot tau d tau plus linear PTO damping of delta Z dot T minus Fm is given as minus to plus infinity eta of tau Ke excitation force T minus tau d tau, the memory effect. We call this equation number 2 for this specific slide. Therefore, friends, in this equation, Z double dot T and Z dot T are time dependent acceleration and velocity of the bodies present in the device. For example, the floats, okay. Eta is the free surface elevation. Now, I can also modify this equation of motion with cross coefficients resulting from the multi-body interaction. So, the equation of motion, what we wrote in equation 1, can also be modified by including the multi-body dynamics. In that case, the mass matrix, including the dry mass and added mass. So, now we are writing the mass matrix including the dry mass and the added mass, which can be expressed as what you see on the screen here. This becomes the dry mass and this becomes the added mass. Okay, you can see this is 6 by 6 equation which is having both the concepts added together in the mass matrix. Okay, for a typical float with multi-body dynamics, that is with adjacent floats connected to the central body. The details of this formulation can be seen from the research papers what we published on wave energy converters with different journals. I would request the listeners to please look into those original publications and see the derivation of this mass matrix and the added mass matrix completely from the first principles. So, let us say for the paucity of time, we will say that this can be expressed as you see on the screen here. Okay. So, now this is the mass matrix term for the central buoy. Okay. This is the mass matrix term which includes added mass also. You can see here the added mass. Okay. So, added mass is included with the dry mass. Okay. This is for the central buoy. Similarly, we can also write down the radiation damping. The radiation damping matrix which is CRF for the float and CRB for the buoy. This is for the floats This is for the central buoy. Okay, one can write these two values also as you see in the screen here. So, this is for the float and this is for the buoy. So, one can generate these two equations and then this becomes an input for the characteristic equation of motion in weakly formed nonlinear time domain model in WEC-SIM-II. Okay. Furthermore, friends, we know that the mass of the float, dry and of the buoy are included in the formulation. They have also included the solid moment of inertia of the float and the moment of inertia of the central buoy in the formulation, and these are all done for the formulation of n number of floats, where J is the number of count of floats. So, this will help you to frame the problem with multi-body dynamics. Okay. So, friends, the surge, pitch, on sway and roll and vice versa are neglected in the formulation. The surge, pitch on sway and roll are neglected. To make the problem much more simple, okay, the number of floats acting in the whole composition also accounts for the gap between the each layout. So, the number of floats considered also accounts for the gap between them in the layout, in the float layout. So, that is a very important interference effect. If you remember, we said something called Q factor, which is to be included in the analysis. Of course, friends, viscous effects neglected in the formulation. And only radiation contributes to the hydrodynamic damping. Okay. So, therefore, we can straight away say the radiation force in the device in any degree can be said as, if it is for the central buoy, it is referred as ACC PQ. If it is for the motion of any one specific float, if it is motion of any one float in the whole arrangement, then we should say this as A F J F of PQ. That is how we will read this matrix. Okay, that is how we read this matrix. That is how we read this matrix. Right. Having said this, the float's interaction in every step is captured. in each step of iteration is captured, and we include something called the memory effects in the analysis. We already saw the equation of motion formulation, which can be represented as the radiation impulse response function and so on. The radiation component Kr is the total radiation force coming on the system, which is defined by the nonlinear response and the net effect of Kr on the device. Okay. The radiation damping can also be a part of the Cummins equation. The hydrostatic stiffness components offering by the Moore lines is also coupled to the mass and the damping matrices. Okay. For example, I should say the hydrostatic stiffness variation of the mooring lines is also coupled to the mass and stiffness of the system. So, therefore, the mooring stiffness matrix can be given by this equation as you see on the screen. So, this is my mooring stiffness matrix. Which is identified as Km in the problem formulation. So, I should say Km here, given by this, which can be seen in many of my papers on TLPs as well as on floating structures. So, the basic derivation of this mooring stiffness is similar to any positive buoyant system, for example, tension like mooring system of a TLP, which can be seen in a classic thing. Okay. Therefore, friends, the mooring length becomes unstretched the mooring length being unstretched also undergoes change in tension. Okay. So, this can be also captured. This can also be captured to investigate or assess the fatigue life. So, this will tell you the reliability of the device status in the C state installed. Okay. So, now I want to connect the time domain to frequency domain, which we have done. So, the frequency domain and the time domain can be connected for the excitation and radiation terms. Let me do this. So, the excitation term, let us say the heave wall 3, whether it is for a central buoy or for a float, jth float, as a function of time can be said as 1 by 2 pi minus to plus infinity E I omega t F E, what you get as 3, whether it is a central buoy or a float of jth number I omega d omega. Equation number 4. Similarly, for the radiation kernel, Kr in the heave direction, whether it is for the central buoy or for the jth float, as a function of time can be connected to the frequency domain as 2 by pi 0 to infinity. We take only the positive side of the curve as Cr33, whether central buoy or the jth float, which is going to be of omega cos omega t d omega. So, equation number 5. So, in this above equation, this K I W, okay, is seen as frequency dependent complex exciting force. Similarly, in this equation, Cr omega is the frequency domain radiating force. Okay, that is how we read this equation. So, now once this is understood, we can move on to the WEC-SIM block diagram to understand how this can be input in the WEC-SIM to find out the behavior as you see in the screen here. So, this becomes my WEC-SIM block diagram. For the model taken. So, one can see closely this figure, the hydrodynamic properties of the floats are fed into the model. The rotational PTO occurring from 4 floats, F1, F2, F3, F4, there are 4 floats here. Okay. The rotational damping coming from these floats are also fed as an input to the system. So, this becomes a system input which we get from frequency domain. Okay. Then this is connected to the hydrodynamic characteristic of the central buoy, which is a typical figure fabricated for the experimental study, and then the hydrodynamic characteristic of the central buoy is also controlled by the mooring stiffness of the lines which are connected to the system. Okay. So, the whole system now is handled as a floating buoy of 6-degree freedom system model. So, that becomes my WEC-SIM block diagram, which is now ready for my analysis in weakly nonlinear time domain frame, which is actually handled in WEC-SIM, which is an open source software. So, friends, I hope this lecture gave you good mathematic intensity as well as understanding the concepts of how WEC-SIM is being used in the weakly nonlinear time domain model. So, we will take you forward to the experimental studies which are used to compute the damping coefficients of the PTO mechanism, and then how the whole design was optimized to get the maximum absorbed power in the design system as an example study what we took at our research team. So, I hope these lectures and the corresponding reference papers will be helpful for you to understand the basic formulation of an wave energy system from the first principles. Thank you very much. Stay connected. Namaste.